Hey guys, so in this question we have two infinitely long current carrying wires. They carry currents I1 and I2 as shown in the diagram. The equations of the wire curvatures are y squared minus 8x minus 6y plus 25 is equal to 0. So this is a parabolic equation curve. And the other one is x is equal to 0, right? So these are your these are your two infinitely long current carrying wires. One is along x is equal to 0 and the other one is along y squared minus 8x minus 6y plus 25 is equal to 0, which is the equation of this parabola. The magnitude of force acting on one of the wires due to the other is mu naught I1 I2 by beta, right? So we need to calculate the force acting between the two wires. That's given in the form of mu naught I1 I2 by beta. We need to calculate what the value of beta is over here, right? So once again, these are your two infinitely long current carrying wires. One is in the straight, one is a straight current carrying wire. The other one is a parabolic wire. We basically need to calculate the force acting between them and give the answer in this form, right? Okay, so this question can be made slightly easier if we take care of the equation of the parabola first. So that's how we'll start attempting this. But ideally, we will try to calculate what's the force acting on I2 due to I1. We'll calculate the force acting on this parabolic current carrying wire due to the straight current carrying wire, right? And we need distances and all that sort of thing. So that will be easier if we once analyze what the equation of the parabola is. So the equation of the parabola here is given as y squared minus 8x minus 6y plus 25 is equal to 0. So I can rewrite this as y squared minus 6y plus 9 is equal to 8x minus 16. So that will become equal to y minus 3 whole square is equal to 8 into x minus 2. So this is your equation of parabola. And this tells me that the vertex of this parabola is located at the point 2, 3. So the closest distance it has from the straight line is 2, right? So to make this slightly easier, I'll again transform it back to the origin. So I'll write this equation of parabola as y squared is equal to 8x itself. And let me shift my diagram to this sort right now. So now I'll say that the vertex of the parabola is located at 0, 0 itself. I'll say that the vertex of the parabola is located at 0, 0 itself. And your your straight current carrying wire is passing through the point x is equal to minus 2. So this is the way I'm imagining the diagram right now. This is your parabolic wire whose equation now is y squared is equal to 8x. And now I'll say that the straight current carrying wire is passing through x is equal to minus 2. Hence making the diagram same as before. I'm just making it slightly mathematically easier. Right. So now we'll calculate force on I2 due to I1. We'll calculate force on this parabolic wire due to this infinite current carrying wire right now. And the force on I2 is due to the magnetic field of I1. I1 will create magnetic field at all these points. And if you notice, the distance between these points is not the same. Your parabolic wire is at different distances from this infinite current carrying wire. So here we'll have to make use of integration only. So we'll take a small portion, we'll calculate the force acting on a small portion, and then we'll add up the force acting on all those portions over here, right? So let me take one small portion having a length dl, right? So your dl bar will be equal to dx I cap plus dy j cap. So I have two variables over here. So to make this easier, we'll be writing your x and y coordinates of a parabola in parametric form. Your x and y coordinates of a parabola can be written as 80 squared comma 280 for equations of a parabola in the form of y squared is equal to 4x. So your parametric form here will become equal to 80 squared comma 280. So here a value is 2. So this becomes equal to 2t squared comma 40. I can now write, instead of having two variables y and x, I can now convert it into one variable over here, which will make my calculation simpler. So I can write dl bar over here. So x is equal to 2t squared. Your x coordinate is 2t squared. Your y coordinate is 4t. So dx will be equal to 4t dt. dy will be equal to 4 dt. So dl bar will be equal to 4t dt I cap and dy is equal to 4 dt j cap. Right, so this will be your dl bar. This will be a dl bar in terms of one variable itself, and that is t. And what will be b bar value? A b bar value will basically be equal to, b bar is the magnetic field due to the infinite current carrying wire. So your magnetic field with the infinite current carrying wire just depends on the x coordinate over here. Just depends on the x coordinate. So that'll just be equal to mu naught I1 divided by 2 pi r. But your r value now will become equal to 2 plus 2t squared. 2 plus 2t squared. And the direction of magnetic field will be along minus k. Right? So now I'll substitute all of this in this expression. df bar is equal to I into dl bar cross b bar. So substituting them all in that expression, I'll get df bar is equal to I here is I2 into dl bar is nothing but 4t dt I cap plus 4 dt j cap. So this is your dl bar cross b bar. B bar is nothing but mu naught I1 divided by, I can take 2 common from this, so it becomes 4 pi of 1 plus t squared of minus k cap, right? So I could have made use of some symmetry over here. If you already notice your minus, I have a minus I cap component here and I have a plus I cap component here, right? So you will see that the I cap component, or that is the I cap cross minus k cap, which will give me the j cap component of force, that will get cancelled, right? That will get cancelled. You will also get the same from integration as well, if you're able to notice symmetry over here, because I'll have the same magnetic field at this point as well as at this point, but your dl bar, your I cap component is in opposite direction. So your force due to the I cap component of current will get cancelled at these 2 points, whereas the j cap component of current is the same in both the cases over here. So effectively we can ignore this part. Effectively we can ignore this part right now. So your net force will only be acting due to this component. Your net force will only be acting due to that component. So I just need to integrate that component over here. So your df bar then will become equal to, just taking that component, it will become equal to so mu I dl, so I2, it was I2 into 4 dt j cap cross mu naught I1 divided by 4 pi of 1 plus t squared, 4 pi of 1 plus t squared of minus k cap. Right? Hopefully it's clear why we are not taking the I cap component, because that is anyways going to get cancelled from integration. So this is your df bar value. So this will become equal to mu naught I1 I2 into dt divided by pi of 1 plus t squared, divided by pi of 1 plus t squared. And now this force is acting along minus I cap. So this is your df bar right now. So what will be your net force? Your net force then will become equal to integral of this, integral of mu naught I1 I2 into dt divided by pi of 1 plus t squared, from minus infinity to plus infinity. So this will, your t value varies from minus infinity to plus infinity if you're writing it according to the parametric form. So this becomes equal to mu naught I1 I2 by pi. Integral of dt by 1 plus t squared is equal to nothing but tan inverse of t. It will become equal to tan inverse of t. So this becomes equal to just tan inverse of t, with the limits of t varying from minus infinity to plus infinity. So this becomes equal to mu naught I1 I2 by pi. Tan inverse of infinity is pi by 2. Tan inverse of minus infinity is minus pi by 2. So the force expression basically becomes equal to mu naught I1 I2. So this will be a value of force acting between these two wires. So according to your answer, your beta value has to be equal to 1, right? So a good question, a good mathematical question here. The maths was slightly difficult in this question, but hopefully you guys got this. I'll see you guys in the next question.